Okay, so the very first thing that we want to do when we're analyzing our data is we want to find JASP. So hopefully now you've all downloaded JASP, which is a free software from the internet. JASP can be found if you just type it in to a browser, it'll come up. And the latest version can be found here. You can download it for Windows, for Mac, and for Linux if you're one of those people who uses Linux. I'm using a Mac, so I would download this. I would just click on it and download the DMG file and then follow the instructions for downloading as normal. If you're having difficulty installing something, let me know and I can help you out. Alright, so I've already installed it and I can type it in and it'll come up. And so that's what I'm going to do. JASP will open up. You can see it's bouncing up and down in the corner here. It's going to take a few seconds to actually verify and open JASP. My computer's a little bit slower because I've probably got too much stuff on it. It's also trying to compile and load a video. So this is not a great thing to be doing while you're trying to teach a statistics class at the same time. So maybe I should create this one later. Some of you have actually come across this and you've had issues with this before. So this is actually a good thing that I've had this error now and I can tell you about it. So JASP can't be opened because it's from an unidentified developer. This happens sometimes when you download stuff from the internet. You need to tell your Mac that it's okay to open it. So just go to Finder in that case, find your applications, and then look for JASP. JASP is going to be somewhere, probably in alphabetical order. Say open, wait for it. It's going to start to try and open, and then it's going to ask you, are you sure that you want to open this program? And then you say, yes, I'm quite sure that I want to open this program. I trust this program. So now it's going to open, and then we can get on with the analysis. All right, so when JASP first opens, this is the interface that you're going to see. JASP is built on top of the R programming language. R is a wonderful programming language, but it's a bit advanced for right now. Most of these analyses that you'll see here are common. They're what we've been talking about. So in our course, we have talked about descriptive statistics. We spent about 1 or 2 chapters talking about that. So things like the mean and the standard deviation can be found in here. We've also talked a little bit about correlation. Correlation can be found under this regression panel here. It's got the handy image to actually point that out. The next thing that we're going to be talking about is t-tests. And t-tests are comparisons for when you do not know the population level mean and standard deviation, which is the case here. So this is all very well, but how do we get the data into our JASP? Well, luckily, I have downloaded the data. Sorry, that's a pop-up brain for you. Luckily, I have downloaded the class data from our website under the essay page. And there's, at the very bottom, there's a download link, and it says class data wide. Click on that, download it. The format of the data is something called a CSV file. CSV stands for comma-separated values. If you open it in a text file, or a text document, you can actually see that all of the things, all of the items are separated by commas, and every time there's a comma that denotes a new column. So you can see ID, sex, congruent, accuracy, congruent reaction time, incongruent accuracy, incongruent reaction time. And all of the different values here are separated by commas. This is extraordinarily difficult to read. So you can also open it using something like Microsoft Excel. Microsoft Excel is actually the default program to open a CSV file, and it knows exactly what to do with all of the commas. So you can see now it's beautifully formatted, we can read it, and it looks pretty good. Okay, so here we go. That's great. We know what is in our file. We have ID, sex, accuracy for the congruent trials, accuracy for the incongruent trials, reaction times for the congruent trials, and reaction time for the incongruent trials. So that is good. All right, let's close this for a second. I'm not going to save it. And we're going to go back to our JASP program. Now let's load in the data. I'm going to look on my computer for this particular program or this particular data set, and I know that I have it somewhere in teaching. So I've got a folder for teaching under York, Psych 2021. I have it in the essay folder, and I have it under class data wide. So I have that. I'm going to open it, and here we go. JASP knows how to read in CSV files. If you have your data in any other format, it won't read it. So don't change the format that is on the class website. It's already in CSV format, and it's going to be easy for JASP to use. So you'll notice that a lot of these icons are actually on the top of the columns here. So you have rulers on top of some of them, and you have sort of Venn diagrams on the other. The rulers indicate that this is a continuous measurement. The Venn diagram, on the other hand, means that this is a categorical measurement, and that's exactly right, because here we have continuous measurements of reaction time and accuracy, and we have a category, male or female. All right, so the very first thing that you're going to need for your paper is you're going to need descriptive statistics. So handily, that's under the tab that says descriptives, and then you just click on descriptive statistics. And the things that you will want descriptive statistics of are all of the continuous measurements. So I would select all of them and just click on the little arrow that moves them over into variables. You can see immediately that JASP generates a very nice table that is very nearly the table that you would want to put in your paper. It has congruent accuracy, incongruent accuracy, congruent reaction time, and incongruent reaction time. You might want to move these around so that the accuracies are next to one another, and we could do that by simply doing something like that. Now you've got the reaction times together and you've got the accuracies together so that they're more easily comparable. You can see that we have some common descriptive statistics that we've talked about, the mean and the standard deviation, and we've also got the minimum and the maximum, so we do have a measure of the range as well. You'll notice that there are also some plots that you can access. There's a tab for plots. So you can click on that. And we could actually get box plots. So the thing about a box plot is that it will give us, per variable, a measure of the center, the median, and it'll give us the interquartile ranges as well as any outliers. And you can see immediately that there's one person who's a ginormous outlier in terms of the accuracy on the congruent trial. Most people are very close to doing perfectly on this trial, but this person is performing at chance. That suggests that this person is actually button mashing. Button mashing is a scientific term for somebody who is disobeying your instructions to be careful and vigilant, and they're just pushing a button randomly rather than actually paying attention to the task and pushing the button that corresponds to what they're supposed to be pushing. So this person will need to be identified and removed before any further analyses can be done. And you should actually say that this is the case in your methods or under your participants section. You can also see that you have a couple of people here who are outliers. You might want to inspect whether this person is one of them, etc. So one thing that we notice is because the hypothesis is about gender or sex, we might want to split this data by sex, and we haven't done so yet. The way that we would do that is actually to highlight the sex item here and move it into the split variable over here. So we can do that, and as soon as we do it, you'll notice that the table and the plots instantly update, and now it's split by gender. So you can see that we have 35 women and 16 men. Instantly you should be thinking, well, only 16 men. That limits the inferences that we can make about our data, but nevertheless, you're still going to persevere. We can also see now that this one man who is really, really inaccurate is part of the men group, or the male group. So, it's a guy, surprise, surprise, that's throwing all of the data off. So you're going to need to get rid of him. All right, once you've done that, then you're going to go back and you're going to actually edit you're going to edit your sheet. and this keeps on coming up. So what I would suggest that you do is you make a copy of the raw data. So I'm going to actually do this now. I have class data wide copy, and I'm going to say, I'm going to name it something meaningful, and I'm going to say no outlier. Why do I make a copy of the data? Well, it's not strictly speaking necessary in your case because the data is online and you can download it again. But what happens if you're collecting data for real? If you simply remove the data from the raw data set, you will have altered the raw data, and it's potential that, that was the only copy of the data in existence, and you've just deleted data. That is a terrible, terrible thing to do. You never want to do that. So get into the habit of making a copy of the data and only editing a copy, and never editing the raw data. Okay, so we need to find this person who scored in the 50s or 60%, and there they are right there. This person should be removed before we actually analyze the data. So we will, there we go, they're gone. And this is again the copy of the data that we're using. I'm going to save this, and then we're going to reload it into our data. So now let's open our data again. I'm going to browse. And now I have class data no outlier. I'm going to open that. And here we go. It's loading. I'm going to rerun the descriptive statistics for exactly the same way as I've done them before. And I'm going to split it by gender and create box plots. All right, so now we can see that, yes, while there are a couple of men who now appear to be outliers here, I wouldn't necessarily remove them because everybody's performing above 86% accuracy. They're doing quite well. So even though you've now identified or you've shifted the criterion for what is an outlier, aside from that one person it was extraordinarily justifiable to remove them because they were performing at chance. You have less of a good reason to remove these people because they're still doing the tasks. They're still performing at 86% accuracy. So you would have a harder time justifying to, I don't know, people in journals why you should remove these people. Okay, so we've got our descriptive statistics, and you would probably in the paper want to report your number of valid, number of men, number of women, and the means and standard deviations for each of these types of tasks. The next thing that we want to do is we want to see whether congruent accuracy, incongruent accuracy, congruent reaction time, and incongruent reaction time actually differ by group. Recall that congruent accuracy is when you actually had the task matching the mapping on your hand. The two tasks matched. So the shape filling task and the filling task and the shape task were actually matching. So if they were assigned to the right hand, then you would respond with both of those to the right hand. The incongruent is when the mapping did not match. So you might have a triangle and two dots, and one of those, the triangle might be a response with the right hand, and the two dots might require a response with the left hand, but depending on whether the shape was above or below the line, you had to respond with one of those. So that would be an incongruent trial, and that would be much, much harder. Anyway, what we expect to see is that incongruent trials will be much slower than congruent trials. So we can test that. So let's have a look, and we're going to run something called, first of all, a paired samples t-test. A paired samples t-test we can use to assess whether there is a difference between the accuracy on the congruent trial and the incongruent trial. So we could do that, and we can actually see that, yes, indeed, there does appear to be a difference here. There appears to be, and you can see that what it's doing is it's taking the congruent accuracy and it's literally subtracting incongruent accuracy, and you get a t-statistic that is 7.88. What we can ask for is we can ask also for an effect size. This is remember this is in standard deviation units. The p-value is how likely it is to observe the difference that we've observed by chance alone if the null hypothesis is correct. And the null hypothesis would be that there is no difference between these two things here. There's no difference between the incongruent accuracy and the congruent accuracy, and clearly that is not the case. We also would like to get some descriptives and some descriptive plots. So the descriptives are going to be a repeat of what we had earlier up here, but it's nicely contextualized for this particular analysis. And it tells you something about the mean for each of the conditions. So here you can see that on average, people were about 5% more accurate when it was a congruent trial than an incongruent trial. Okay, well that's great. What about reaction times? Well, we would predict that very likely it is the case that people will take longer on incongruent trials. That is, they'll hesitate more, and they won't be as fast. So we're going to do the exact same thing with reaction time, and it actually builds it into the table as we're looking at it. So here we can see that yes, we still have a statistically significant result. It's less than 0.05. And the Cohen's d-value is not quite as large now, so it affected accuracy more than it affected reaction time. But it's still 0.3 standard deviations, which is still quite, well, it's a moderate effect size. We also get the descriptive statistics for the reaction time, and we can see that people took about 30 milliseconds longer on the incongruent reaction times than they did for the congruent trials. You can also see that the spread is much larger. So if you're looking at the accuracy here, you have a very precise estimate of where the center of the distribution is for each of these. And what are these? These are 95% confidence intervals, which means that if we were to run this task 100 times, then 95% of the time the true mean would be right where we think it is, or it would be within these bounds. These are also 95% confidence bounds, but they're much wider. So even though we have a significant difference between these groups, we are less certain about where the true mean would be for the reaction time in the long run. All right, so now we have essentially verified that the task is working. We verified that, yes, indeed, we have a difference between incongruent and congruent trials, and that the incongruent trials are much more difficult than the congruent trials. What we could do now is we could actually look to see if the hypothesis is borne out. What I'm going to do is I'm going to head back over to our data set, and I'm going to actually create a new variable. This new variable, if I go back into teaching, York, winter, essay. All right, so with no outlier, yes, open it up. What you might have noticed is that we're actually interested in the difference between these things. So we could actually calculate the difference between the accuracy trials here. So we're going to say incong minus congruent accuracy. And then we can also say incong minus congruent reaction time. So the difference between these things, and you can say equal. If you want to do this quickly, you can just type in a quick formula in Excel, say equals, and we're going to look for the incongruent accuracy. So the incongruent accuracy is over here. Subtract, and the congruent accuracy is over here. And we're just going to do that. So to the extent that you have a larger negative number, you were more affected by the incongruent task. So you were more adversely affected by the incongruent task. So these are all mostly negatives, which means that for the most part, people did not do better. In fact, nobody did better. Except for that person. That person's a weirdo. But you still don't have justification to remove that person. So on the whole, most people do worse on the incongruent task relative to the congruent task. And that's exactly what you showed with the paired t-test. we're going to do the exact same thing with the reaction times, and you'll see why in a minute. It's going to cut down the number of comparisons that you do when you look at gender. So now we're going to look at incongruent minus congruent, but for reaction time. So again, we're looking at the incongruent here, and we're going to subtract from that the congruent reaction time, and you're going to get negative numbers again. These are milliseconds, so this is the amount of slowdown that you're actually experiencing when you are actually looking at this task. So if you are looking at the incongruent task here, it looks like this person was actually faster on this particular task. So if you have a larger number, then that means that they were slower. So you should, on the whole, have larger numbers here. This person slowed down quite a bit. Some people were faster, so that's interesting. But on the whole, on the average, you do have larger numbers on the incongruent reaction times than the congruent reaction times. And this fits with what we saw. The fact that there's more variability in this particular set of columns rather than everybody being less accurate, or nearly everybody being less accurate, fits with what we saw as well, the confidence bounds being larger. Okay, so now that we've calculated these two different scores, we can save this again and open it back up in JASP. So let's go to JASP, and we're going to open it again. Computer, browse, and we're going to open it. So now, when we open it this time, you should notice that we have our two extra columns, the different score here and the different score here. All right. Notice that when we did the descriptive statistics, we calculated the descriptive statistics for the raw scores, not for the different scores. The descriptive statistics for the raw scores tell the reader exactly what the distributions look like for all of those, because it can be a little bit harder to interpret different scores, but it'll make sense if we do a t-test on this. So the very first thing we want to do is we want to navigate to t-tests, and because we have two groups which are independent, that is, being male or female does not affect whether other people in the other group are male or female. These are independent groups. We're going to click on that. What we want to look at is we want to look at our two difference scores here. We want to look at incongruent minus congruent reaction times. And we also want to look at incongruent minus congruent accuracy. So move those over. Now it's not actually calculated anything. It's pre-populated the table, but it hasn't calculated anything, and that's because you need to tell it what the grouping variable is. And in this case, sex is the grouping variable. Now you can see it's working. It's trying to calculate it. And we have no significant difference here. That's interesting. All right. So what you also want to calculate is an effect size. And you can see here's the t statistic, the degrees of freedom, the p-value 0.118, and Cohen's d. A Cohen's d value of 0.49 is actually relatively large. It's a moderate effect, so you would probably want to say something about that, even though we did not achieve a significant difference. The reason that we didn't achieve a significant difference is probably because we have, so few people in the males group. So it looks like this is trending towards significance, and if we had a priori expected that there would be a group difference, for example, group 1 greater than group 2, you might have been able to select a one-tailed test, and that's done this way by selecting group 1 greater than group 2. You could also select the opposite, which would be group 1 less than group 2, and you can see how that changes all of the numbers. We can't do this post hoc, because I did not expect that there was going to be a difference necessarily, but you could justify that potentially based on the paper that we were using. Okay, we're also going to ask for descriptive statistics here, which you're going to report along with your outcomes, and descriptive plots. So we can see the descriptive plots, and for reaction times it looks like the difference for women is slightly larger than it is for men. So women, it appears, are going to be slightly slower, or the difference between incongruent and congruent reaction times is slightly larger for women than it is for men. That is not what I would have predicted, but there it is. All right. There's no difference, or it appears that there is no difference between incongruent and congruent trials for accuracy by gender. All right. So this is essentially the set of data that I would include. You would have to incorporate it with text into the set of data or the results section, and then I expect you to discuss it in the discussion section. If you have any further questions, feel free to email me.